Uh, can you see the question paper? I shared the screen.
Yes, yes.
Yeah, just look at the first question paper here. The first question that they asked, sorry. Okay. Here, draw and explain the full load phasor diagrams of single phase transformer for lagging, leading, and unity power factor. This will comes in practical transformer on load. We'll start now. And also second question, just observe, develop the equivalent circuit of single phase transformer and show the parameters of primary and secondary winding may be combined to give a simplified equivalent circuit referred to primer set. So these two are the questions that we'll be going to cover in this class. So first we should know that we discussed ideal transformer features and ideal transformer on no load and practical transformer on no load. So today we are going to discuss about practical transformer on load with the help of phasor diagrams, and also we'll cover equivalent circuit diagram of single phase transformer, how we'll be going to simplify the equivalent circuit diagram, and also how we'll be going to get the clear idea about with the reference of primary side as well as the secondary side, and we'll solve some problems even. So this the single three phase transformer advantage will comes in second chapter of first module. I will discuss later. And also this is 2B is Scott connection that is explained with the circuit diagram and phasor diagram. How two transformers connected in open delta can supply the power successfully. This will come in the second chapter. We'll discuss later. And coming to the next question paper. So here, can you see the second question paper?
Yes.
So here, explain operation of practical transformer on load. That will be going to explain now. Also draw the phasor diagram. And the second one is this will comes in second chapter, that is on three phase transformer. That is some derivation show that open delta connection has a kVA rating of 58% of rating of the normal delta connection, and also list the limitations of open delta connection, and this problem will solve later. And the regulation phasor diagram, and this will later. So just observe one question you can expect, either practical transformer on no load or is practical transformer on load, and also equivalent circuit diagram of transformer. Out of three, either one or two questions they will ask in examination for 6 to 8 marks, so that we have to practice and we should be perfect in these questions. Then there will be nowhere you will be having the chance to lose the marks for this. And this is the third question paper, and here this is June July 2017. So the help of phasor diagram, explain the operation of practical transformer on load. So the common question you will be getting from three question paper is practical transformer on load. So by chance they may ask practical transformer on no load, also the ideal transformer on load. Also the features of ideal transformer, only 4 points will be there. Already discussed in last class. There will be resistance is 0, losses will be 0, and input power is same as output power. And also you can get ideal response V1 equals to E1. And write a short note on all-day efficiency. I will explain later. And this problem also will discuss. This will becomes in a second chapter, that is for three phase star 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 delta. There are some 5 connections. Very easy to understand all the 5 connections of transformer. We'll discuss later. And these are some questions. So I can observe for this all 3 question paper. So the common question is practical transformer on load. So you can expect practical transformer on load, or else no load, or else ideal transformer no load, and also the features of ideal transformer that we discussed in, we already discussed in last class. So just a glance, what and all we discussed last class. So some basics of transformer and types of transformer, and also losses in transformer. We discussed some EMF equation and also the condition for maximum efficiency, that is iron loss equals to copper loss. After that, we discussed about this ideal transformer. So zero winding resistance, zero leakage flux, and no losses. If they asked you to explain the ideal transformer on no load, you have to draw this diagram and you have to draw the phasor diagram. By taking flux as a reference, IM is in phase with the flux, and this V1 leads phi at an angle of 90 degree. Similarly, E1 is anti-phase with the V1, and E1 and E2 are in phase with each other. This E1 and E2 will lags the flux phi at an angle of 90 degree. Similarly, on no load of practical transformer, so there will be no load current will be having two components. One is magnetizing component, other one is core loss component. So magnetizing component which will be responsible to produce flux. Similarly, core loss component which will be having the function of this is the losses under no load condition. So here since there is no load in a practical transformer, so that the copper loss will be zero, only will be getting the iron losses in a transformer, that we can also call this as core loss. And also while drawing the phasor diagram, flux is the reference first point. I hope you remembered that we discussed in last class already. So here the flux is the reference. So by taking this flux as a reference, this flux is the reference. By taking this, IM is in phase with the flux. First, we should get the value of I naught. I naught is the addition of IM and IC. So that IM is in phase with the flux phi. Later, V1 leads the flux phi at an angle of 90 degree. Then IC is in phase with the V1. By adding IM and IC, you can get I naught. And similarly, E1 is anti-phase with the V1, and E1 and E2 are in phase with each other, and this E1 and E2 which lags the flux at an angle of 90 degree, whereas the direction of this phasor diagram is anti-clockwise direction. So these all we discussed in the last class, and here we discussed some points regarding with the help of this phasor diagram, we are going to write the value of IM and IC. How we'll be writing IM? With the help of velocity components. IM is given by, how you write?
I naught.
I naught.
I naught sin omega, sin phi naught.
IM is I naught sin phi naught. Similarly, IC is I naught
I naught cos phi naught.
cos phi naught. So this is under no load condition. So now we are going to discuss about practical transformer on load condition.
No.
No load finished. Now we'll be going to discuss about practical transformer on load
On load.
condition. So can you see the slide now?
Yes.
Slide ಕಾಣಿಸ್ತಾ ಇದೆನಾ?
Yes, sir.
Okay. So this is the diagram. You just have to note down before noting down the diagram. So I'll just explain what and all will be happening in practical transformer on load. So here,
This is no load, sir. I can see no load one.
you are seeing this one where PDF.
No load. Yes.
Okay. I'll change now. Now can see, right?
Yes.
Practical transformer on load.
Yes, can see.
Okay. So this is a practical transformer on load. So before going to start the explanation of this practical transformer on load, so if there is no resistance and leakage reactance, as you asked last class, sir, is there for ideal transformer on load? If there is no resistance and leakage reactance, then you can consider this as ideal transformer. If there is a load, then it is practical transformer. Fine. If there is no load means ideal transformer on load. If there is a load, practical transformer on load. So just nothing to worry about ideal transformer on load. Concentrate on this practical transformer on load. Here will be first to draw the phasor diagram. There are two phases. One is with the help of winding resistance and leakage reactance, and other one without winding resistance and leakage reactance. So here on load, so there are two transformers you can see here on load. So just look at the first one. So this is the first one. So for this transformer, so if there is a load means first I would like to explain the operation of transformer. So here V1 is a supply voltage. V1 is supply voltage of the transformer. Whenever the supply is given to the primary side of the transformer, so the current starts to flow. So this is current flows to the primary side, that is I1. Current starts to flow, that is I1. So whenever current flows through this transformer, which induces flux or which produces the flux. So how we'll get the direction of flux? So with the help of thumb rule, if there is a direction of current, if this is the direction of current, so this will be the direction of flux. I think you are seeing the video. So if this is the direction of current, so now current is traveling from left side to right side in your slide. So current is traveling from left side to right side. So this is the direction of current, so that the flux direction is upward. So that the whenever the voltage supply voltage is given to the primary winding of the transformer, I1 starts to flow in primary side of the transformer. So due to this flow of current, we can get the direction of flux. This is the direction of current and this will be the direction of flux, so that the main flux direction will be upward. So here this is a main flux direction. This will be upward. This will be the main flux. You can observe this direction. The direction of this flux is upward and which will be traveling. So this is coming back to the primary side of the transformer again. So whenever this flux links with the secondary side of the transformer, whenever this flux links with the secondary side of the transformer, current I2 will be induced. I2 will be induced in a second side of the transformer, or else I2 will be starts to flowing through the load due to the linkage of the flux from primary winding. So that this is the direction of current I2 towards load. So again, with the help of this on practical transformer, the secondary winding also produces its own flux. Secondary winding also produces its own flux. Again, how will we get the direction of flux? The current will be flowing from left side to right side, so that the direction of flux is upward. So this is the flux which will be produced in produced due to secondary winding. So this will be the secondary flux. You can observe here the direction of the flux. So this will be the secondary flux as the arrow indicates. Secondary flux phi 2. Clear? Any doubt with it for these two fluxes and the direction of fluxes? So first what we are going to do, we'll be going to give a supply voltage. So due to this supply voltage, current induced in primary side. So again, we can get the direction of main flux as a upward direction, as the current flows from left side to right side from left hand rule. The direction of flux will be, that will be the motion of the motion of the flux will be upward. That will be linked with the secondary winding. Due to that, current will be induced in the secondary side. Again, this will be gives the current I2. Again, the direction of I2, with the help of this, you can get the direction of flux phi 2. You can denote this as phi 2 is nothing but secondary flux. So now we just observe these two. So here the flux phi 2 direction and main flux direction, this will be the main flux direction. Sorry, this will be the main flux direction. This will be the direction of main flux. Similarly, the direction of secondary flux I2 will be this. So you can observe this. Now here the phi 2 which opposes the phi. Phi 2 which opposes phi. Yeah. Phi 2 which will be opposes the main flux phi. One sec. Give me a second. I'll come. You just take down the diagram of this first one. You take down the diagram of this first one. I'll back. Okay.
Okay. Okay.
Finished with it. Shall I start?
Yes. Yes.
Okay. So now what I'll just clamp again on the first diagram. The voltage is V1 will be applying. Current starts to flow. Due to that, the main flux is produced. The direction of main flux is upward. So this main flux links with a secondary winding. So due to that, secondary winding which produces its own flux, that is secondary flux phi 2, and the direction of that secondary flux is upward. Now we just compare both the fluxes. The main flux and secondary flux will be in opposite direction. So now I'll talk about this current I2. So I2, where it is flowing now? I2 is flowing through. This will be flowing to.
Primary.
No, where
Primary.
it is flowing I2? I2 is flowing through.
In secondary.
No, the
Or
direction.
to the load.
To the load. I2 is flowing to the load. So now the nature of this I2, or else the I2 value, this will be depending on load. Okay, so now there are three types of load will be knowing. One is resistive load, inductive load, and capacitive load. Did you heard this? There are three types of load will be using given in your lab. One is resistive
Yes.
load, other one is inductive load, and capacitive load. If the load is inductive load, or else if the load is resistive load, so I2 and voltage across load, I can write here it as V2. So V2 is voltage across load, or else voltage across secondary winding, or else voltage across load, it will be V2. So if the load is resistive in nature, I2 and V2 are, do you know the phasor diagram? If the load is resistance,
In phase.
yes, if the load is resistance, I2 and V2 will be in phase with each other. If the load is inductive load, if the load is inductive load, I will write, if the load is inductive, I2 lags V2.
That's V2.
If the load is inductive load, then I2 lags V2 at an angle of 90 degree, or else at an angle of phi 2, you can see. If you don't know the angle, you can write as phi 2. Okay. If the load is capacitive load, how can write? Suppose if the
I2.
load is capacitive load,
V2 lags I2. Voltage lags current.
voltage lags current. Here also voltage lags current, no, in inductive load.
Current lags voltage.
Sorry. So in case of inductive, current lags voltage. In case of capacitance,
Voltage lags current.
voltage lags current, or else you can say it as current
Current
leads
leads voltage.
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 So this is a very important thing you should remember to draw the phasor diagram, or else to understand the nature of load. So there are three types of load. If the load is resistance, voltage and current are in phase with each other. If the load is inductive in nature, current lags the voltage at an angle of phi, to else voltage leads the current at an angle of phi. If the load is capacitive in nature, current leads the voltage, or else voltage lags the current at an angle of 90 degree. Okay, so then there is exist, I'll just clear this field. So by knowing this, now there exists a secondary MMF. Secondary side, this will be produces MMF, that is a secondary MMF, that is represented by, what is the formula of MMF? Do you know that? MMF formula? Don't know? MMF is given by N into
N9.
I,
L.
and its unit is, SI unit is ampere turns. This will be, unit will be represented by ampere turns. This will be the unit of MMF. Okay, so MMF is given by number of turns into current flows to the secondary. So now there exists a secondary there exists a secondary MMF N2 I2. So number of turns in secondary winding is N2. So this will be having number of turns N2. Similarly, on the primary side, it will be having number of turns N1. So if you want to get secondary side MMF, means N2 into I2 will get secondary MMF, that is N2 into I2. This will be the secondary MMF, due to which secondary sets up its own flux that will be the opposite direction. Okay, so now we can call this N2 and N2 I2 as demagnetizing ampere turns. Remember this, we can call this N2 I2 as demagnetizing ampere turns, or it's a demagnetizing MMF. This you can see here, demagnetizing MMF. So the flux F2 is momentarily reduces the main flux now. So this is opposite direction. This will be the direction of main flux. Similarly, the direction of secondary flux will be phi 2 will be opposite direction. So this secondary flux phi 2, which reduces the main flux because it is opposite direction. So that too will be in opposite direction, so that the main the secondary flux phi 2 will be reduces the main flux, so that due to which the magnetizing component, so due to which the magnetizing due to which what will happen, if phi 2 reduces the phi 1, means automatically the EMF will be reduces, that is E1 will be reduces. This E1 will be reduces. E1 will be reduces, so that the vector difference between V1 and E1, vector difference is nothing but V1 minus E1, V1 minus E1 is increases due to which primary draws more current from the supply. So I'll just explain once again from the starting. First, what we have to know will be giving the supply voltage V1, the current I1 is produces. So due to that, we can get the direction of magnetic flux, that is a main flux phi as a pole direction. The main flux will be linked with the secondary winding. So due to that leakage of the fluxes, the demagnetizing MMF will be produces. So due to that demagnetizing flux, current I2 is induces, and which will be produces the flux at a secondary side, that is the secondary flux phi 2. So that will be opposes the main flux. So now here phi 2 opposes main flux, you can see here. So whenever this phi 2 will be opposite to the main flux, So this phi 2 trying to reduce the main flux. So now this will be trying to reduce the main flux. So if the main flux reduces, EMF induced in primary winding also decreases or else reduces. If E1 reduces, if this E1 reduces, then difference between V1 and E1, difference between E1 and E1 will be increases, so that I can say it as the primary current draws more current. This primary current draws more current, so that I'll write this primary current draws more current. Okay, so what is that more current? So that we need to give what? Additional current, additional current drawn by the primary winding. So due to the load, hence you can call it here, uh, hence called a load component of primary current. So now I have to denote load component of primary current is denoted by I2 dash. This will be the additional current. Okay, so this is represented by I2 dash, and this I2 dash is always antiphase with the I2. I2 dash will be antiphase with the I2. Antiphase is nothing but opposite. Antiphase is nothing but I2. If the I2 dash is downward direction, then I2 will be upward direction. So that is nothing but your antiphase. I2 dash is always antiphase with the I2. So this sets up its own flux again. I2 dash will be sets its own flux, that is phi 2 dash. So now what happened? So first, in first diagram, two fluxes produces, one is main flux, other one is secondary flux. So due to that secondary flux, main flux is reduces. If the main flux reduces, why it is reduces? Because both are in opposite direction, so that due to that secondary flux phi 2, main flux will be reduces. So whenever the main flux which reduces, then EMF induced in the primary winding will be reduces. If the EMF in primary winding reduces, EMF in a primary winding reduces, then difference between V1 and E1 will be increases. So when the difference between supply voltage and EMF induced in primary winding increases, then which means that this will be draws the more primary current, so that the current flows to the primary winding will be, which needs extra additional current. So that extra additional current is nothing but your I2 dash. Clear? That extra I2 dash is nothing but your primary current. So that this is the additional current I2 dash. Why you have to give additional current I2 dash? Because phi 2 opposes phi, due to that E1 reduces, due to that E1 V1 minus E1 will be increases, so that it requires extra additional current I2 dash. Clear?
Yes. Yes.
Okay. So now what we are doing? So in the first diagram, you are seeing the main flux phi and secondary flux phi 2. So addition of this main flux phi, in the case of first diagram, so we'll be adding additional current, additional primary current, that is I2 dash. So whenever there will be addition primary current, I2 dash will be applying to the same transformer. For the same transformer, we'll be applying additional current I2 dash. So this will be produces its own flux, that is phi 2 dash. Again, what will be the direction of phi 2 dash here? Direction of phi 2 dash. What will be the direction of phi 2 dash?
Phi 2.
Hmm?
Opposite of phi 2, that is downwards.
No, I2 dash will be applying here, right? This is the direction of I2 dash. Okay, so it will be produced.
So you asked I2 or phi 2?
That's what this I2 dash produces a flux called it as phi 2 dash. Okay, I2 dash produces flux phi 2 dash. So what is the direction of phi 2 dash here?
Phi upwards.
Yes, this will be the direction of I2 dash. So that the phi 2 dash direction will be upward. So earlier we already have two fluxes right here. One is phi 2, other one is phi. Apart from this, the additional flux will be produced due to additional current I2 dash. So that phi 2 dash will be produced. So you can see here in a diagram. See here in a diagram, this is the direction of your phi 2 dash. Okay, this is phi 2 dash. You can see here more flux is nothing but additional flux phi 2 dash. Okay, so now can you tell me what are the two fluxes will be in same direction in this diagram? One is phi 2 dash and other one is
Phi 2.
no. What is the same direction I'm asking? Phi 2 dash is also in upward here and
Yes.
phi is also upward, right? Main flux.
Yes, sir.
So this
Yes.
is phi 2 dash and this is phi. So these two are in same direction. If the fluxes are in same direction, then there will be a addition of flux. Okay, then there will be a addition of flux. So by adding this phi 2 dash and the main flux phi, we can reduce what? Secondary flux phi 2. Only one flux will be flowing in opposite direction here. You can observe. One is phi 2 and phi 2 dash and phi will be in same direction, but phi 2 will be in opposite direction, so that by adding these two fluxes, we can eliminate this flux. Understood?
Yes.
Understood. So now
Yes,
what
sir.
happened? Now the flux will be constant. Now the flux will be constant. So now whenever the flux is constant, so now again what will happen? Thus for any load, this flux phi 2 dash neutralizes phi 2. You can observe, as just now told, this phi 2 dash neutralizes phi 2. How will be neutralizes? Because by adding phi 2 dash and phi, that will be removes the flux phi 2. When it eliminate the flux phi 2, so now the MMF in ampere turns on primary side and secondary side will be equal. MMF means magnetomotive force on primary side and the secondary side. So I just now written, how can you write the magnetic, MMF on MMF in secondary side? MMF is given by on secondary side. How will write?
Into I2.
N2 into I2.
I2.
Similarly, how will write in primary side?
N1 I1.
Look at the diagram properly. Whether the I1 is flowing
Sure.
or
Or N2 dash.
no. This is N1. Okay. And here it is N2.
N1, N2. Here N1 I2 dash.
Yes, exactly. So on primary side, what will be the MMF? N1 into I2 dash.
I2 dash.
So now the flux is constant, so that I can write both the MMF are equal, the balanced. Now on the primary side and on the secondary side, the MMF will be balanced. So I can write here as N1 into I2 dash equals to, I think you are writing N1 into I2 dash equals to, what will write?
N2 into I2.
N2 into I2. So how will write I2 dash now? I2 dash is given by
N2 I2 by N1.
N2 I2 by N1, or else N2 by N1 into I2. Okay.
I2.
So N2 by N1 is nothing but
Okay.
K. So that I can write
Concentration.
I2 dash equals to K into I2.
I2.
Here, that you note down now. That expression you note down.
Yes.
So N1 into I2 dash equals to N2 into I2. So that you write the I2 dash. I2 dash is given by N2 by N1 into I2. So write what is N2 by N1? That is nothing but K into I2. K into I2. Finished?
Yes, sir.
Now tell me, so when there is no load, when the practical transformer on no load, so it will be having no load current, right? That is I naught.
Current, yes.
What are the two components that I naught have?
IM and IC.
IM and
Magnetizing
IC.
and
You will be writing I naught equals to IM plus IC,
IC.
right? Similarly here, this is a primary current I1 on load, practical transformer on load. This primary current I1 has two components again. Can you tell me what are those? One is no load component and other one is load component. So that this I1 will be having two components. One is no load component, that is nothing but how will be right? No load component, that is nothing but I naught plus second one is the load current. What is the load current here? Load current is nothing but this additional current. So this is nothing but I naught plus I2 dash. Note down this. Here I1 is given by I naught plus I2 dash. And now tell me this I2 depending on what? This I2 is depending on?
Side.
Yes, this I2 is depending on? This will be depending on?
Load.
Load. How can you write the I2 and V2 if the load is resistive load?
Are in phase. V1
V2 and I2 are in phase with each other. If the load is inductive in nature,
then current lags voltage.
If the load is capacitive load,
then current leads.
Current leads the voltage. Okay. So now here you return that I1 is given by I naught plus I2 dash, right? So how can you write I naught here? I naught is given by
I1 plus.
No, I naught is nothing but no load current.
IM plus IC.
Yes, I naught is given by IM plus IC, right down. And what is the value of IM? How will write IM?
I naught sine omega phi naught.
I naught sine phi naught. Similarly, IC is given by
IC I naught cos phi naught.
I naught cos phi naught. So this is what you have to remember for practical transformer on load. So okay, they can also call this as MMF balancing. Sometimes they will ask questions like explain practical transformer on load, or else they will ask in the examination explain MMF balancing on practical transformer. MMF balancing, because you're doing MMF on primary side and MMF on secondary side, will be making it as balance. Balance means what? Both side will be equal. That is, this is your MMF balancing. That is N1 I2 dash equals to, this is on primary side and this is on secondary side. So when the primary side, this will be balanced. Whenever there will be addition current which flows to the primary side, then the primary side of the MMF will be balanced. Why we need to give additional current I2 dash? Because if there are two fluxes on a transformer, say it has secondary flux phi 2 and phi 1, the direction of this phi 2 and main flux phi will be opposite direction, so that this phi 2 will be reducing the main flux. If the main flux reduces, E1 reduces, that is EMF induced in primary winding will be reduces. If E1 reduces, then difference between this V1 and E1 will be increases. If the difference between V1 and E1 will be increases, then it requires additional primary current that will be flows to the load. So that will be required I2. So whenever the additional current which will be gives I2 dash, it produces its own flux, say it as phi 2 dash, then this phi 2 dash and main flux, that is phi 2 dash and main flux phi will be neutralize the secondary flux phi 2, then it will be making MMF balancing on left side as well as right side. That is nothing but on primary side as well as on secondary side. That is nothing but N1 into I2 dash equals to N2 into I2. Clear with the, if you have any doubts, you can ask now if you're not understanding also.
Yes, sir. The first diagram shows the here we got MMFNI, right?
Where?
Uh, it's, the first diagram, sir.
Okay, this diagram. Hmm.
Uh, yes. In that we found MMF, and then after that we got to second diagram, no, sir.
So in first diagram, we'll be getting only MMF on secondary side. What is that? N2 into
Second side.
I2. Okay, this is we'll
Yes.
be getting MMF on secondary side. So now what we are doing, we'll be making the secondary side MMF will be same as primary side MMF. So now it is not same. This is not same. This primary side MMF will be not same as secondary side now. Why? Because fluxes will be in opposite direction, right? So if the fluxes are opposite direction, I want to make this primary side as equal. The MMF will be balanced. I have to do primary side MMF will be balanced, but I can't do in a first diagram because both the fluxes will be produced, both the fluxes will be in opposite direction. So that I have to neutralize any one fluxes, any one flux. So I can't give supply to the secondary side because the secondary side is connected to load.
Load.
So that what I am doing, I'll be giving additional current to the primary side. Why I am giving additional current to the primary side? Because this phi2 will be reducing phi. If the main flux reduces, EMF induced in primary side will be decreases. If the EMF is decreases, then the difference between this V1 and EMF induced in primary side will be increases. Okay,
Increase.
if this is increases, then current will be increase. That is nothing but it requires additional current to balance MMF on primary side. So that what I am doing, I am giving additional current I2 dash. So now what will happen with the help of this additional current I2 dash? Again, it produces its own flux, right? That is phi 2 dash. Now with the help of this what? Two fluxes are in same direction. One flux
Same
in
direction.
opposite direction.
Opposite.
Okay. So now if the fluxes are in same direction, then there will be addition of flux. This is main flux and this is additional flux phi 2 dash. So these two fluxes will be adding. When these two fluxes are adding, these two are having higher value than this flux. So that what will happen by adding this phi 2 dash and phi, the phi 2 will be neutralized. Also you can say it as will be eliminating phi 2. So now the constant flux is flowing in a transformer, right? So why the constant flux is flowing? Because we'll be applying the additional current, right? So now after applying the additional current, the flux is constant. If the flux is constant, we already know MMF in secondary side, that is N2 I2. So now I can write here MMF in primary side, that is N1 into when it is balanced by applying the additional current, so that I can write here MMF is given by N1 into I2 dash.
Yes.
Clear?
Yes. Yes.
Any doubts now?
No.
Okay. So now this is just theory now. You have to write the theory as with the help of this diagram. So you have to understand the theory by looking at the diagram. Once after looking at the diagram, you have to remember the theory of this practical transformer on load, or else you can also call this as what? MMF balancing. MMF balancing of practical transformer. So now we have to draw the what? Phasor diagram. So before drawing the phasor diagram, it is connected to the load, right? It is connected to the load. So how much phasor diagram I can draw now?
1, 2.
How many loads are there?
1 load.
How many types of loads are there?
3 types.
3 types. One is?
Resistive, inductive and capacitive.
Yes, exactly. So how many phasor diagrams I have to draw now?
3.
3. So first I have to draw the phasor diagram for resistive load. So this I2 is depending on load. If the load is resistance, I2 and V2 will be in phase with each other, right?
Yes.
If the load is inductive, I2 lags P2. If the load is capacitive, I2 leads V2. So now coming for this phasor diagram for 3 different loads. Okay, so now what is the first step? I'll explain this resistive load. Okay, so you try to explain for the inductive load. Listen carefully and understand.
Yes.
Okay, so now what is the first step here?
Phase phi
Hmm?
should draw flux.
Should draw flux. So for this flux, sorry, first what you have to do, you have to take the reference. So this is your reference, that is flux phi. Clear? So next what you have to do,
EM.
you already know 50% of phasor diagram in last class, right?
Yes.
So the first step is reference, that is flux. Flux is the reference. Second point, which is responsible to produce flux?
IM.
IM. So where you have to write IM?
On phi.
IM is in phase with the
In phase
flux phi.
flux.
So first step is reference, phi is reference, right? Second step is IM is in phase with the flux
Flux
phi.
phi.
And third point is
V1.
V1. V1. So this is the direction of your phasor. So next step is V1.
Lags.
Yes, V1 lags or leads with respect to flux.
Lags.
See the direction of the phasor. So this is the direction of phasor. Whether it is lagging or leading with respect to phi, which is first here?
Lead.
Don't be confused with it. This is the direction
No,
of.
sir, it is.
See the direction of phasor, anti-clockwise, right?
Yes.
Flux is here. Okay. So V1 is here.
Lags, sir.
Which lags which? Tell me now. Either IM lags V1 or V1
Phi
lags
lags.
IM. Yes, phi.
IM lags V1.
Okay, IM or phi,
Lags
both are
V1.
same. So phi lags V1. Third step. Third step is phi lags V1 at an angle of 90 degree. Third step over. And what is the fourth step? I have to write IC. IC is in phase with the V1. Practical transformer on load. Last class. Can you remember?
Yes.
So now I want to get what? I naught. Because primary current I1 is given by, what is I1 current in practical transformer on load? Just now I told I1 is given by
I naught plus.
Yes,
I2
exactly. I naught plus I2 dash. So in a phasor diagram, I want to draw primary current I1, so that I want to, if you want to write I1, I want to get I naught and I2 dash, right? But I2 dash is always antiphase with the I2. I2 dash is antiphase with I2. But I naught, how will get I naught? I naught is having two components again. One is IM and the other one is IC. Okay, so it will be having IM and IC. So I want to write I naught. So if I want to get I naught, means I have to do the what? Vector addition of IM and IC, so that I have to get IM and IC. IM is in phase with the flux phi and IC is in phase with the V1. So now I will do vector addition. I'll get what? I naught. Clear?
Yes.
If you have doubt, now only clear. Okay, don't be confused. Don't be
No.
confused. Same as practical transformer on load. 50% same as practical transformer on load. So how will be writing on load? Sorry, on no load will be not having I1, only will be having I0. So that you will be drawing only till I0. Here we just have to what? Add the I1. So first step, flux is reference. Second step, IC is in phase with the flux. You can draw along with this explanation. Sorry, IM is in phase with the flux phi. And third step, phi lags V1 at an angle of 90 degree. Phi lags V1 at an angle of 90 degree. And the fourth step, IC is in phase with the V1. IC is in phase with V1. Okay. And the next step is by adding this IM and IC, I can get I0. By adding this IM and IC, I can get I0. Clear?
Yes. Yes.
Shall I move to the next step?
Yes.
Okay. So now, the load is resistive load, right? Load is resistive load.
Resistive.
So now, what is the condition of I2? I2 is depending on load. If the load is resistive load, I2 is in phase with the V2, right? I2 is in phase with the V2. So here we'll be not considering any, here there will be considering, assuming that it will be having no winding resistance and leakage reactances. So that what I am doing, instead of V2, here I'll write I2, and I2 will be in phase with the E2. I2 will be in phase with the V2, that is E2. I2 is in phase with E2 because the load is resistive load. Before writing this I2, I want to get E1. So E1 and V1 are equal and opposite direction according to which law? According to which E1 and V1 are equal and opposite?
Lenz.
Yes, according to
Lenz's law.
Lenz's law, E1 will be opposite to the V1, and E1 and E2 are in phase with each other. Clear?
Yes. Yes.
So now the load is resistive load, so that I2 is in phase with the E2. I2 is in phase with the E2. So I2 dash is always anti-phase with the I2. So that I'll get, if you getting the I2, then I2 dash you can get. I2 dash is anti-phase with the I2. I2 dash is anti-phase with the I2. Clear?
Yes. Yes.
Clear? So now I have,
Yes,
so now I have I0 and I2 dash. Shall I get I1 now?
Yes.
I1 is given by
I0 and I2 dash.
I0 and I2 dash. So that I have to do what? Vector addition. So how will do the vector addition? From the tip of this I2, draw a line which is parallel to the I0. From the tip of I2, draw a line which is parallel to the I0. Okay. Similarly, from the tip of I0, draw a line which is parallel to the
I0 to
I2 dash, right?
yes.
Then at some point they'll be intersecting these two lines. Then from the origin, just draw a line for the intersecting line. So this represents your I1. Clear?
Yes.
Clear?
Yes, sir.
Yes. Can you explain once?
Yes, sir. First step is finding the flux
And
reference
sorry,
axis.
so wait 1 sec. So while drawing the phasor diagram, you write here, you mention where is IM and where is IC. Here they were not mentioned. you mention, then it
Hmm.
will be help you to understand easily.
Yes.
Okay, now tell me. And also angle between this I naught and V1 is phi naught. No load angle. Angle between I naught and V1 is phi naught. Same as practical transformer on load, on no load, last class. Similarly, angle between V1 and I1 is phi 1. 1 represent on load. Primary current of the transformer when the transformer is on load. Okay. So now can you explain?
Yes, sir.
Yes. Start.
Uh, First, reference axis, that is flux, we are drawing, and then which is responsible for that is IM,
Hmm.
so which is in phase to flux. Then V1 leads phi, so that which is 90 degree.
Okay.
Then we are drawing IC.
Hmm.
Yeah, and then we are drawing IC, which is in phase to V1,
Yes.
and there will get vector addition of IM and IC, that is I naught.
Okay.
And then we are getting the E1 and E2, which is antiphase to V1,
Yes.
which is in opposite direction to V1. Then we are getting I2, which is again in phase to E2.
Yes.
Then we are getting I2, which is I2 dash, which is antiphase to I2.
Yes.
And we are getting the vector sum of I2 dash and I naught.
Yes.
This is I1.
Yes. And one more point is this E2 and E1 lags the phi at an angle of 90 degree. So this E2 and E2 which lags the phi at an angle of 90 degree. Always the direction of phasor is anti-clockwise, then you can easily get which is leading and which is lagging. Okay. Similarly, here the same explanation, only the difference is inductive load. If the load is inductive, what will happen? If the
Current
load,
lags.
yes, I2 lags E2. If the load is inductive, I2 lags E2. Can you tell me? Can you try to explain this? Same
The
procedure.
above one is same. Phi we are drawing. Then IM.
Yes,
Uh, then with V1 leads phi
yes,
by 90 degree.
yes.
Then the opposite of V1, that is I2, E2.
E2 and E1 are in phase.
Yes, E2 and E1 are in phase. Then we are drawing I naught.
Okay.
Yeah,
You missed
we will
IC.
get I naught. Yeah, IC also. IC is in phase with V1.
Hmm.
So IM and IC, the addition of that I naught will get.
Okay, I'll explain now. You just listen carefully and understand. You try to explain. Okay. So the
Yes.
first step is phi is the reference. Second step is IM is in phase with a phi. Remember, the second step is IM is in phase with a phi because it is responsible to produce flux. And the third step is V1. V1 leads phi at an angle of 90 degree. Third step. And the fourth step is IC is in phase with the V1. And the next step is by adding this IM and IC, you can get I naught. Okay. And the next step is E1 is antiphase with a V1 according to Lenz's law. And E1 and E2 are in phase with each other. And the next step is as the load is inductive load, so that this I2 lags E2 at an angle of phi 2 because the load is inductive load to represent on secondary side. So if the load is inductive load because the load is connected on secondary side, so that I2 lags E2 at an angle of phi 2. So I2 dash you can get, that is anti-phase with I2, you can get I2 dash. So once if you get I2 dash, then add I0 and I2 dash, you can get I1. Then the angle between V1 and I0 is phi naught, and angle between V1 and I1 is phi 1. Clear?
Yes.
Yes. Now you can try.
Oh, first we are drawing phi, then IM is in phase with phi,
Yes.
then V1 leads phi by 90 degree,
Yes.
IC is in phase with V1,
Yes.
then we get the vector addition of IM and IC, that is I0.
Yes.
Then we are drawing E2, which is opposite to V1.
Yes.
E1 and E2 are in phase.
Yes.
Then I2, which I2 that is
Yes.
lags E1.
Yes. I2 lags E2.
Yeah, E2. Yeah,
Hmm.
I2 lags E2 by
At-
phi 2 angle.
Yes.
Then we are getting I2 dash, that is opposite of I2.
Okay.
Then we'll add the vector addition of I2 dash and I0,
Yes.
and we are getting I1.
Yes, exactly. This is right. And can you tell me for capacity load? Only the difference is I2 leads V2, or else I2 leads E2. The same explanation. We just tell.
Yes, same
Okay.
thing, phi. Then I am in phase with phi.
Yes.
V1 leads phi by 90 degree.
Yes.
I see in phase to V1.
Yes.
Then I am and I see addition of that is I0.
Yes.
Then E1 and E2, that is in phase and opposite to V1.
Hmm.
Then I2 leads E2. I2 leads E2
Hmm.
by phi 2. Then I am and I0 and I2 dash,
Hmm.
we are getting the vector addition.
Yes. Clear? Any
That is
doubts?
I1. Yes. No.
Just and don't forget to tell the angle whenever you'll be getting. Okay. Angle between
Okay.
E2 and I2 will be, I2 is, what is angle
Phi
between
2.
I2 and E2? Phi 2. Similarly, angle between V1 and phi I0 is
E1 and I0 is phi 0.
phi 0. And angle between V1 and I1 is
E1 and I1, phi 1.
phi 1. And what is the meaning of I0?
I0 is load current.
No load current.
No load current.
No load primary current. Okay. And what is the meaning of I1?
I1 primary current.
Primary current. And what is the I2 dash?
I2 dash is secondary current.
Hmm?
Additional primary current.
Yes, load component, or else primary load component of primary current. Load component of primary current. Okay. So this is about phasor diagram when there is no winding resistance and leakage reactance. Okay. So again, we'll be having the phasor diagrams. Before that, that I will explain tomorrow, the phasor diagram. Okay. So now I'll just take the equivalent circuit. Okay. So there are again three, I think you were seeing the slide. So you have to draw for different loads, for unity power factor load, and also for lagging power factor load, and also you have to write it for leading power factor load. I'll explain this phasor diagram. It is very easy. Once if you're understanding this phasor diagram, that is, one second. Once if you're understanding these phasor diagrams, then you can easily understand the phasor diagrams of load. Okay, this I'll explain tomorrow, because after finishing equivalent circuit diagram, we can easily understand the phasor diagrams on different loads. That is for these three loads. Okay, so first for the equivalent circuit. Uh, are you audible? Can you hear?
Yes, sir.
Okay. So here the equivalent circuit means here the combination of fixed and variable resistance and reactances. Resistance and reactance is nothing but you can also say it as impedance. Impedance you are writing it as R plus JX. R plus Jx, and that plus and minus that will be depending on load. If there is an inductive load, you can write here it as R plus Jxl. If there is a capacitive load, you are writing here it as R minus Jxc. You already know this, and which exactly simulates the performance and working of the machine. Here machine is nothing but transformer. Transformer is a static device and it is used to transfer power from one place to other place by changing voltage and current and without changing the frequency. So now for a transformer, no load primary current I naught has two components. No load primary current I naught has two components, and what are those?
IM, IC.
Im and Ic. So one is Im, that is given by I naught sine phi naught. You can say it as magnetizing component. And what is the function of Im?
IM, which produces flux.
Yes, which is responsible to produce flux. And the next is IC, that is given by cos phi naught. You can call this as active component, or else you can call it as core loss component, is given by I naught cos phi naught. So now we can see no load equivalent circuit diagram. We just draw along with this. So no load means I am not going to connect any load on the secondary side. Okay, so that the input voltage is V1 is applying, and whenever the voltage V1 applied, the no load primary current starts to flowing. What is I naught? I naught has two components, that is Im plus Ic. So that here I naught is flowing according to KCL, it is dividing. According to KCL, it is dividing. So one current which is IC and other current is IM. So now I think you'll be getting doubt now why they are connected resistance when there is a IC and why they are connected X naught when there is IM. So what is the function of IM here?
To produce flux.
Flux. Where it is producing the flux, where there is a coil, there is a flux. Where there is a coil, there is a flux. So Im which flows to the reactance, Im which flows to the reactance, that is X naught. Clear?
Yes.
Similarly, IC means what? IC means can you hear?
Yes, sir. Yes.
IC means what?
IC is active component.
That is core loss component or else active component. Okay.
Yes.
Core loss.
Yes.
Core loss means loss. When the loss which produces, I am always telling that where there is a resistance, there is loss. Where there is a resistance, there is a loss. So that this core loss component will be flowing through the resistance because it has to produce losses so that there is a resistance. So here Im which has to produce the flux so that which will be flows to the coil. By adding this IC and Im, we can get I naught again. Clear? Any doubt about this diagram?
No.
So now tell me how we'll be writing IC. So voltage across parallel component is same. Voltage across parallel combination is same. Here this is supply voltage V1. So that voltage across R0 is also voltage across R0 is also
V1.
V1. Similarly,
V1.
voltage across X0 is also V1 because voltage across parallel combination is same.
V1.
Okay. So how we'll write IC now? By applying Ohm's law, IC is given by
R
hmm?
I C. V by R.
V or V1?
V by R.
V1.
V1 by R naught.
V1 by R naught. Similarly, how will write IM? IM is given by
V1 by X naught.
V1 by
IM
X.
is equal to V1 by X naught.
Yes. So that is what
J-
you will be getting here. R naught is given by V1 divided by IC and X naught is given by V1 divided by IM. Clear?
Yes.
Understanding?
Yes, sir.
Okay. So now, when the load is connected to the transformer, this till here, when there is no load, if there is no load primary current will be there. So that will be having two components, IM and IC. So with the help of that, we'll be drawing the no load equivalent circuit. This is no load equivalent circuit diagram because secondary side is not connected to the load only. So that I'm not drawing the secondary side. So now when there is a load, suppose if there is a load is connected to the transformer, then secondary current I2 flows. Secondary current I2 flows. So this causes two drops. One is a resistance drops. Sorry, one is resistance drop, other one is reactance drop. So that this causes voltage drop across R2 and X2. So due to I2. So when it is produces, when primary current draws additional current I2 dash, as we already know why it is producing the additional current means we have to do the what? MMF balancing. So that to do the MMF balancing, so you already know I2 dash equals to I2 divided by K. Okay. And I1 is the phasor addition of I0 and I2 dash is also known. So now we have to draw the phasor diagram, sorry, the equivalent circuit diagram. Okay. So now look at here in the equivalent circuit, windings are not shown, but it is further simplified by the transferring all the values to the primary or to the secondary. So which means transferring all the values to the primary or secondary means either it is referred to the primary winding or else it referred to the secondary winding. Okay. So now you can see here this you also draw along with this. V1 is supply voltage, primary winding. So here there is a load, so that it is having resistance and reactance. You can also call it as R1 and X1 is connected in series. You can say this as Z1. Z1 is given by R1 plus or minus JX1. Similarly, this R2 and X2 is forms, Z2 is nothing but R2 plus or minus JX2. So now I'll start from beginning. So whenever the supply is given, I1 starts to flow. So what is I1 here? Primary current. So primary current I1 is given by what? Just now we finished on load.
V1.
No, I1 is given by, just now while drawing the phasor diagram, I1 is given by
I0 and I2 dash.
I0 plus I2 dash.
I2 dash.
So this is I1. Okay. So I1, so which is given by adding I0 dash and I2 dash. So that I0 is flowing here and I2 dash will be flowing here. That is additional primary current. So now this I0 is given by
IM plus IC.
IM plus IC. So that I can write here IC and IM. So IM is flows through the coil. Why?
IM to produce flux.
To produce flux. Similarly, IC is flowing through the resistance. Why? Because IC means IC means no load core loss.
And
To produce loss, where there is a resistance, there
yes,
is a loss. So that here, so it will be come to here. So again, this I2 dash is nothing but additional current will be flowing through the primary winding of the transformer. Primary winding of the transformer. It is having number of turns N1, and that will be coming back to the supply. Primary side clear?
yes,
Clear?
yes,
And EMF induced in primary winding
yes,
is E1. This is on primary side. Similarly, on secondary side is connected to the load with the help of winding resistance and reactance, that is R2 and X2 to the load ZL. ZL is nothing but impedance load. So ZL is nothing but either it is inductive load, or else it is capacitive load, or else it is resistive load. So depending on the nature of this load, the current I2 will be varying. This is I2 is flowing here. So this I2 is depending on load. If the load is inductive load, this I2 lags V2. If the load is capacitive load, I2 leads V2. If the load is resistive load, I2 and V2 are in phase with each other. So that V2 is nothing but terminal voltage, also voltage across load. And with the help of this, it will be induced as secondary EMF E2. Clear? Draw ಮಾಡ್ಕೊಂಡ್ರೆ ಆಯ್ತಾ? Next slide ಹೋಗುವ.
uh,
Okay. So this is equivalent
yes,
circuit of transformer. So the next we'll be going to simplifying this equivalent circuit. So equivalent circuit refer to primary. So refer to primary means referring to the primary side means you have to transfer all the secondary side. So I'll tell here only. So refer to primary means, so I'm going to referring this is a primary side, right? And this is a secondary side. So refer to primary means I'm going to shift all these values on secondary terminals, that is R2 and X2 and V2 and the load ZL. I have to transfer all these values to primary side. I have to write in terms of primary. Understanding? I have to write all these R2, X2 and E2, V2, ZL. I have to write in terms of primary. I have to transfer this to the primary side. So that means refer to primary. Suppose if you can say it as a refer to secondary winding. So refer to secondary means I have to write all these primary side values in terms of secondary, means I have to transfer all these parameters on the primary winding to the secondary side. So which means that it refers to the secondary. So now, so to refer the primary, you have to transfer. So while transferring, what will happen? I'll talk about the refer to primary side. So for the primary side, I want to transfer this R2, X2 and this E2 and also V2 and this ZL to the primary side. I have to transfer this to here, this side. So now I'll be going to neglect this winding. So now there is no winding. I'm neglecting the winding. I'm transferring these values to the primary side so that R2 becomes R2 dash. Okay. So I'll be transferring this to the primary side. I'm connecting directly from this I2 to R2 dash. R2 becomes R2 dash and X2 becomes X2 dash. E2 becomes E2 dash. V2 becomes V2 dash and ZL becomes ZL dash. So we have to know what is the value of R2 dash, X2 dash, Z2 dash refer to primary. So R2 dash is nothing but R2 divided by K square. So these are some basics. I think you already know, refer to primary. And R2 dash is nothing but R2 divided by K square. Similarly, X2 dash is nothing but X2 divided by K square. And Z2 dash is nothing but Z2 divided by K square. And ZL dash is nothing but ZL divided by K square. Okay. So now, while transferring values, remember that. So low winding and high voltage winding, that is HV side and LV side. So while transferring the values, remember the rule that, so if there is a low voltage winding, then it will be having high current and low impedance. Suppose if there is a high voltage winding, it will be having vice versa, that is low current and high impedance. So that after transferring, what will happen? See here, look at the diagram. So till here, I will just write the line till here, same as primary side. ಬರ್ಕೊಳ್ತಾ ಇದ್ದೀರಲ್ಲ?
Yes.
Okay. So till here, same as primary side. So that I can write as it is x1, r1, i1, i0, ic, im, i2 dash. So after this, I am transferring secondary side's parameter to the primary side. So while transferring that, r2 becomes r2 dash and x2 becomes x2 dash and z2 becomes z2 dash and e2 becomes e2 dash. That would be same as e1 because there is no winding, and v2 becomes v2 dash. Similarly, zl becomes zl dash. So now what is R2 here? R2 is nothing but refer to primary. R2 is given by, sorry, R2 dash is given by R2 divided
R2
by
by k square.
k square. Similarly, x2 dash is given by x2 divided by k square, and z2 dash is nothing but z2 divided by k square, and zl dash is nothing but zl divided by k square. And the primary side parameters as it is, there is no dash, there is no change anything, but only the difference is this in the secondary side. Okay. So if you want to write refer to secondary means how will write?
Oh, everything from primary will be shifted to second.
Yes, shifting to secondary and everything will becomes dash. I1 dash, x1 dash, r1 dash, ic dash, im dash, i0 dash, and v1 dash. So before that, so this is referred to secondary. See here, v1 dash, r1 dash, x1 dash, z1 dash, r0 dash, x0 dash, i0 dash, and here already I2 dash is there. Here already I2 dash is there. If you are transferring to the secondary side means I2 dash becomes
I2.
I2. So that here will be getting I2. And the rest of will be R2, X2, Z2, V2, ZL. Okay. So what is R1 dash here? If it is referred to primary winding, R2 dash is given by R2 divided by K square. Suppose if referred to secondary side, R1 dash is become R1 into K square.
R1 by R1 into k square.
Similarly, x1 dash is x1 into k square. Z1 dash is z1 into k square. ಅರ್ಥ ಆಗ್ತಿದೆನಾ?
Yes, sir.
If you have any doubts, you can ask. Then I will move to the next last simplified circuit diagram.
Yes, sir. You can move forward.
Okay. So now approximate equivalent circuit diagram. So to get approximate equivalent circuit diagram, here shift no load branch. Shift no load branch containing R0 and X0 to the left of R1 and X1. See here. I will consider refer to primary now. So here, which is no load branch? This is no load branch. Can you see? This is no load branch. If you want to write approximate equivalent circuit diagram, you shift this no load branch to the left side. Here you have to shift the no load branch. Understanding?
Yes.
So now I'll be shifting that no load branch containing R0 X0 to here. So this is approximate equivalent circuit diagram. Same diagram. This is refer to primary I am writing. You can also write it for refer to secondary. And this is more than enough, more than sufficient. You just write refer to primary. So for this, shift all the no load branch to the left side of the R1 and X1. So this is approximate equivalent circuit diagram. So now R1 and R2 dash connected in series. So how will write equivalent circuit diagram? R1 plus,
So primary side,
I can write here, this is R1 plus R2 dash.
R2 dash.
Okay, this is equivalent circuit diagram. So it is referred to primary. So this is referring to primary diagram. I am writing this so that I can write here it as R not 1. R not 1. In some of the textbook, they will write here it as R1E, or else they can write R1E. So what do you mean by R1 not R not 1 or R1E means the equivalent resistance referred to primary winding. Equivalent resistance referred to primary winding. Similarly, how can you write this X1 and X2 will be adding X1 plus X2 dash. I can write X1 plus X2 dash as X01 like this. You can write X1E or X01, R1E or R01. See here, same diagram. They are just simplifying. Two resistances connected in series so that I can write equivalent resistance. R1 plus R2 dash is nothing but here R1E. Similarly, X1 plus X2 dash is nothing but here X1E. Understanding? So what you mean by R1E here? R1E is nothing but equivalent resistance referred to
R1 plus R2 dash.
Yeah, equivalent resistance referred to primary winding. Similarly, X1 is nothing but equivalent reactance referred to primary winding.
Primary winding.
Instead of 1E, if you are writing 2E means
secondary side.
Yes, which will be referring to the secondary side. And this is equivalent circuit diagram of transformer. So in the examination, they will ask you to write to refer a primary side or secondary side. So first you have to write this, then you have to draw this is equivalent circuit diagram of transformer. Later you have to draw refer to primary winding, this diagram. Okay, so after this you have to write refer to secondary winding, then you have to write approximate equivalent circuit diagram, that will be this diagram. So then you have to write what? Simplified equivalent circuit diagram refer to primary. If they were asked you to refer to primary, then you write R1E. If they are telling you to refer to secondary, then you can write R2E. That's it. So this is equivalent circuit diagram of transformer. Any doubts, Vidhi?
Oh, the previous slide, sir.
This one.
Equivalent.
Yes. What happened here?
No, equivalent one. Primary side or secondary side.
This one,
Yes.
This one or refer to primary?
No, this is okay.
Just tell me what happened. Yes, you can ask what doubt you have.
Yes, sir. Oh, yeah. Can you take one more slide back? Primary.
This one,
Okay.
Yes.
This is okay. This is afterwards. Okay. Oh, here's X1. Here, this is referred to primary side, means secondary I'm shifting.
Yes.
To primary.
Yes, yes.
Okay.
See, after shifting, R2 becomes R2 dash, X2 becomes X2 dash. What are the parameters in the secondary side? That's dash. Okay. Similarly, do you have any other doubt here in this circuit?
No.
So now we just look at the secondary, refer to secondary. Secondary parameters will be same as it is, right? Primary parameters becomes dash. R1 becomes R1 dash, X1 becomes X1 dash. Similarly here also, this I1 becomes I1 dash. Already I2 dash will be there, so that I2 dash becomes I2. Clear?
Yes.
Any other doubt you have?
No, sir.
Shall we wind up?
What is this E1? E dash equal to K.
We have to either see
K
here.
E1. Yeah.
K is nothing but what? E2 divided by E1. That is N2 by N1 equals to E2 by E1. Right?
Yes, yes.
E2 divided by E1. So if you want to write E2 here, this is referred to secondary side. Right? This is referred to secondary. So E2 becomes what?
E1 dash.
Sorry, E2 is the same. In secondary side, E2 is same. Primary side EMF becomes its dash. So that E1 becomes E1 dash.
Dash.
So that,
E1. Yes.
so I can write K into E1, E2 dash. This is E2. Okay, this is referred to secondary. So that you'll be writing like this. See here it is K into E1. If it is referred to primary side, E2 divided by K. Understanding? E2 dash is E2 by K.
Yes.
If it is on referred to secondary side, E1 dash equals to E2 into K. K into E1. This is nothing but 2 referring the secondary, so that it becomes dash. Any other doubts?
No, no, sir.
Can you practice this?
Yes.
Okay, before winding up, I'll just show you the question paper now. So
Yes.
now we'll just look at the question paper. Yes. See now, first question, draw and explain full load phasor diagrams of single phase full load. Remember, they mentioned full load. So whatever the phasor diagram I explained in today's class, the on load, transformer on load, that is on no load. Full load tomorrow I'll explain. Okay. So this is full load phasor diagrams of single phase transformer for lagging, leading and unity power factor. We'll discuss tomorrow. So second step, see. Develop the equivalent circuit of a single phase transformer, show that parameters of primary and secondary winding may be combined to give simplified equivalent circuit referred to primary side. So you have to draw all the 5 excluding, so all the 5 excluding secondary, refer to secondary. They were not asked any refer to secondary. Okay. So you have to write refer to primary side only. Main equivalent circuit diagram and no load equivalent circuit diagram and refer to primary side. Then you have to write approximate equivalent circuit diagram. Later you write simplified equivalent circuit diagram. That will be last one, R1E, X1E. Till that you have to write. And also here, explain the operation of practical transformer on load. Also draw the phasor diagram. Okay. So today we class. Similarly here, help of diagram explain the operation of practical transformer on load. With the help of phasor diagram they were mentioned, so that you have to draw the phasor diagram, that is mandatory. Okay. So equivalent circuit diagram and transformer, ideal transformer on no load and features of ideal transformer and practical transformer on no load, practical transformer on load. 5 concepts are finished. In that, all the concepts are important. You just have to concentrate on phasor diagrams and equivalent circuit diagram, practical transformer on load and no load. Anyone they may ask. Okay.
Yes.
If you have any doubts, you can discuss now. We'll end up this.
No, sir. No doubts.
Okay, then have a nice evening. Take care.
Thank you.
Bye bye.